Now let's take a look at a Doppler effect problem. For example, we have a car here, and we have a person here. The person's near a wall, and the connection between car and person is perpendicular to the wall, say for example. Now what if the car has a velocity, say at 35 meters per second, and with an angle 30 degrees with respect to the line of car and person? If the car send out a signal of frequency f0, let's make it 1000 hertz for simplicity. First of all, what will the frequency received by this person? Second question is, what is the frequency of the echo heard by the driver inside the car? So assume that frequency heard by this person is f1. Now I want to point out the formula for Doppler effect. New frequency equals to original frequency of V plus VO, or plus minus VO, V minus plus VS. That is the general equation. In this case, the source is the car, source is moving. The observer at this moment doesn't move. So in our case, we will reduce this to V minus plus Vs. But this equation applies to the relative velocity of Vs. Vs has to be along the line of the observer and the source. So therefore, what really counts in this case, which caused Doppler effect, actually is the V of cosine 30. Because this is the direction between the source and the person. Because source moves, the wavefront get compressed, so the wavelengths reduce around this motion direction. Knowing that, then it's easy to find f1. f1 equals to of 1000 hertz as the original frequency. Say for example that speed of sound, in this case again v equals to 343 of meter per second. So that will be 343 meter per second, 343. Now, shall we choose plus or minus? Right now, obviously, the source moved towards the observer. Observer will receive a higher frequency. So we should choose minus for the denominator. Minus what? Minus this 35 times cosine of 30 degrees, because that it is V cosine 30 along the line of the connection. That is the frequency received by the person. Now, any signal hits a boundary, reflect back, frequency will not change. Phase will change depending on this is a movable end or it's a stationary end. So when frequency bounces back, it is still the same. And now the wall behaves like a source. Observer is the driver in the car. So the new frequency received by the driver in the car, let's name f2. In this case, that f2 is based on f1. Again, the problem is if you ask, where is the car now? We have to assume that this happened very quickly. The car is still right here. Otherwise, we have to redraw the line. So if the car is still here and the bouncing back signal is along the line of a connection of a source and observer. So this is the case now. Source is stationary. Observer moves towards the source. So we have this equation that observer moves. So it's a V plus V of cosine. This is the V of the car. We should use this, V of the car. This is the V of the car of cosine 30 degrees. Because now the observer moved towards the source. Source doesn't move, so this is the V. So we have this based on f1, speed of sound 343 meters per second. That speed of car is 35 meter per second times cosine of 30, that is 0.866, and divided by 343, and you will get the frequency heard by the driver inside the car. Let's look at another problem about two submarines. Well, two submarines are on a head-on collision course during maneuvers in North Atlantic. The first sub is moving at 20.2 km per hour, which is this one, and the second one is moving at 94.6 km per hour, which is the other one. The first submarine sent out a sonar signal. Sonar signal means sound wave in water at an initial frequency 1030 Hertz. So the initial frequency this one sent out is 1030 Hertz. And the sonar wave travels at 5,470 km per hour. So that is the speed of the wave inside the water. So that is very, very high. That is 5,470 km per hour. Now we have to assume that ocean is calm, and which means there's no currents. Question number 1. What is the frequency received by the second submarine? The first one sent out frequency of 1030, and it will pick up by the second one. The second one, assume the frequency picked up by second one is f of 1, then what is that frequency? So let's take a look at the situation. F1 is based on f of O, and right now the submarine on the left, let's name it A, is the source, and B is the observer. So the numerator is for the observer. If you think about observer, then you assume the source does not move. So right now the observer moved towards the source. So that is V plus V of B. And then when you judge the denominator, which is about source, then you assume this one does not move, and due to the motion of source towards the observer, and we have V minus, because it receives high frequency, you do minus for the denominator of V of A. This is the frequency received by the first, for the submarine B. If we sub the number, that initial frequency is 1030 Hertz, and this V, we can use the given units, km per hour, and we don't have to change, because as long as the units are same, this should be the sonar wave speed, and plus V of B is 94.6, and for the V of A, that's 20.2. Now, when we calculate that, please pay attention to the sig fig, because this one has no decimal and that one has one decimal. So actually we round up as 95, and this one actually we cut off this 2 and just use 20, because this is 5,470. And we can do the calculation to find what is the frequency received by F1. Now once that the signal hit submarine B, that submarine B will reflect this signal. The signal does not change frequency when it hit the boundary. So this is actually what the purpose of the first one sending out a signal, because it just wants to know if there's anything there and moving. So it sent out initial frequency f of O, and then what is the frequency received by the first submarine? Well, the submarine B now sent out a frequency is still F1, because this is the reflect signal. But submarine A will receive a different frequency, because right now this is the source. Source is moving, and this is the observer. Observer is also in motion. So we have F2 is based on F of 1. Now, the numerator again is for observer. Now, who's the observer? Observer is A right now. So observer is moving obviously towards the source, so it's a plus. Plus what? Plus V of A. A is observer. And then you must know this minus V of B, because the source is moving towards the observer, and observer receive high frequency, so it's minus, but now source is B because the signal actually is bouncing back from B as if sent by B. So if we plug in the number, we will, based on of F1, we have that 5,470 plus V of A, and A we know that is 20.2, so we can just put 20, and the other one is subtract of 95 of kilometer per hour, and all the units cancels because for the speed, if we use the same units and it cancel, this is just a ratio, and we get frequency heard by the second submarine. Now, if I ask a further question, what if the ocean, let's say if there's a current, let's say the water moves at 100 kilometer per hour towards the second submarine, B. If I ask the same question again, what will the frequency received by submarine B? What will the frequency received by submarine A from the reflect signal? We need to think about this problem because the given 5,470 km per hour, this is for sonar speed. This is with respect to the ocean bed, and also same as with respect to the water because water is still. Now the water moves at 100 km per hour towards B. How do we solve this problem? As a matter of fact, we think about this. Well, sound wave traveled in the stationary fluid. That's how we measure the speed of sound. So if that 5,470 is given to a still fluid, imagine that this is the water. Water moves at 100 km per hour. And if this is assumed like a boat and the wave travel inside the boat, it will still keep that 5,470. However, the boat itself moves. So what I'm proposing is that, as a matter of fact, the current situation for F1 should be as if sound travel with respect to the current at 5,470. The current itself travel additional 100 km per hour, so the sound actually travel faster due to this current towards B. So therefore, for this problem, F1 equals to F0, and now formula will be exactly same, but I'm going to use V of prime because the speed of sound change, plus V of B and V of prime minus V of A, everything same except now V prime, speed of sonar signal, is 5,570 kilometer per hour. Alright, when the signal bounce back, now the current is moved still to the right, so the sound will travel slower. So for second case of F2, which is based on F1, the formula will still be the same as before, but now this V is V prime prime, it's a new one. So this time, if we use the same formula plus a VA and V prime prime minus a V of B, that now since it travels slower because sound travel to the right at 5,470, but the current, actually sound travel bounce back this way, and the current is opposite to it. So now instead of 5,400, it will be 5,370 of kilometer per hour. This is when we encounter current, and we have to consider this situation. Then we can get the correct answer for the Doppler shift.